In this video, we're going to talk about resonance structures. So let's look at our first example where we're going to have an alkene looking like this. Now this alkene at the right end is going to have a primary carbocation. This carbon is positive and it's only attached to one other carbon, so it's a primary carbocation. The resonance structure for this is going to be where the electrons in the double bond move one bond to the right, and then the positive charge moves two carbons to the left. So that's all we can do in this structure. Now let's get into some more complex examples to see how this would play out. Let's put the positive charge here. So to draw resonance structures, you can draw multiple, more than one or two. The electrons in this double bond are going to move to this area, and then the positive charge is going to move two carbons to the left. Let's draw it this way. So a resonance structure for this would be looking like that. And we can actually draw more resonance structures than this. The electrons in this pi bond can move to this area, and then the positive charge can move two carbons left. And so what you can also get is this kind of structure. And that's pretty much all we can do for this one. However, let's rank the carbocation situation here to try and find out which one is the most stable. In the situation that we drew first, the positive charge is on a carbon, this carbon, that is attached to only one other carbon. So because it's attached to one other carbon, it's a primary carbocation. In the middle, we had a tertiary carbocation because the carbon that has the positive charge is attached to three other carbons. And then at the end, we had a secondary carbocation. You need to understand the concept that tertiary carbocations are significantly more stable than secondary carbocations, which are more stable than primary carbocations. So it's going to look like this. So the more stable one is going to be this one. And you should memorize that. Now, let's try and look at resonance structures within a benzene ring. And let me draw the hexagon a little cleaner. And we're going to have the positive charge on a carbon on that top right area. So one resonance structure could be that the positive charge moves two carbons this way, and that these electrons move to this bond. So our new structure would look like this. And then we can kind of repeat the same process where the positive charge moves two carbons and then the bonds move one bond, or the electrons move one bond, not the bonds. So these electrons move one over. Everything else in the molecule stays the same. The positive charge jumps two carbons to this area. And then we can have, once again, the same process. The positive charge moves two to this location, the bonds should move 1 there. And that's the last resonance structure we can draw. Now, if you do want to draw one more, you can. But then what you end up with is the positive moves up here, and then these electrons move 1 down over here. And what you're left with is essentially the same structure that we begin with, except that the double bonds are just shifted. Now let's look at a situation like this where we have a negative charge on an oxygen. How can we draw a resonance structure in this sort of situation? So what we can do is one of these electrons, or a pair of these electrons, can come into this bond to form a double bond between the oxygen and the carbon. And then the negativity of these electrons in this area is going to repel some of these electrons, and they're going to go outside the bond and join the oxygen. So what you're going to get as your other resonance structure is, we talked about this oxygen is not going to be double bonded to the carbon, and then these electrons in this bond are going to move to the oxygen, and they're going to make it so the oxygen has 3 lone pairs as opposed to 2, and has a partial negative charge. So what you can notice here is that these are actually the same structures. They're the exact same. But let's go over a different example where they would be different. Let's say we had a sulfur that had a negative charge next to a carbonyl group like this. And the same thing would happen since sulfur reacts similarly to oxygen. You're going to have one of these electrons join the bond between sulfur and carbon, and then the negativity from this area is going to repulse some of these electrons in the double bond, and they're going to move to the oxygen. So the resonance structure would look like this. You have a negative charge on the oxygen as opposed to the sulfur, and the sulfur, because it was previously negative and now it lost electrons, it's going to be neutral, but now it's going to have a double bond between itself and the carbon. Here's a question for you: which one of these structures is more stable? Is it better to put a partial negative charge on the oxygen or the sulfur? So if you look at your periodic table, oxygen is kind of on top, and then sulfur is right underneath it. So we know that atomic size increases as you go down the periodic table. So sulfur is going to be this big atom, and oxygen is going to be this smaller atom. And I should have drawn it smaller. There. If you have a negative charge, is it better for the negative charge to be spread out over a small surface area or a larger surface area? It would actually be better for it to be spaced out over a larger surface area, because that would make it more stable. It would make the negative charge more diluted. So therefore, it's better to put a negative charge on the sulfur. So because of that, this is going to be the more stable resonance structure. how would you draw a resonance structure for this situation? So we know that the positive charge can move up, and then these electrons can move down. What we're going to do is we're going to take one of the lone pairs in the oxygen and join it to this bond next to it, and then the positive charge is going to move 2 spaces up, so it's going to move like that. And what you're going to get is these electrons join the bond, so now it's a double bond. The positive charge has now moved to the oxygen, and the oxygen has 1 less lone pair, so it looks like that. Now the question is, which one of these structures is more stable? One of the factors that you want to look at when determining the stability of some of these resonance structures is whether all of these atoms are obeying the octet rule. The octet rule means that an atom has 8 electrons in its valence shell. In the situation you have right here, the carbon in the center, which I'm going to just draw as an example here, has an OH on top and has 2 other carbons attached to it. Each bond is equivalent to 2 electrons. And so if it has 3 bonds, that's 2 times 3, that's 6. So on the left side, this carbon has 6 electrons. The oxygen, it has 2 from this bond, so that's 2. 2 from this one, so that's 4. 2 from this lone pair, so that's 6, and then 2 here, which is 8. So oxygen on the left side does obey the octet rule, but carbon doesn't. Let's look at the right side. On the right side, this carbon does obey the octet rule because it has 1, 2, 3, 4 bonds, and each bond is 2 electrons, and 2 times 4 is 8. So this carbon follows the octet rule. The oxygen, let's check if that follows the octet rule. The oxygen has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it, so it also does follow the octet rule. And keep in mind that each bond has 2 electrons in it, and each lone pair has 2 electrons as well. Because the structure on the right side follows the octet rule for both the oxygen and the hydrogen, it is going to be the more stable structure.